My talk is on the experimental issues on quantum spin liquid and mod quantum criticality in organic materials. This is the outline of my talk. I'd like to talk about three issues on this title. First, I'd like to introduce several experimental puzzling features on quantum spin liquid in triangular lattice organic materials. One issue is spins, whether spins are localized or itinerant. The second issue is the possible instability of spin liquid. The second issue is that we have a doped spin liquid material in which we observe the pressure-induced non-film liquid to film liquid crossover, and associated with this, BC to BCS crossover in the superconducting state. Finally, I'd like to touch the issue of the quantum critical behavior of the mode transitions, and especially I'd like to talk about the disorder effect on this quantum criticality of a mode transition. And the systems, organic systems, which I'm going to talk about today is like this. It's a material have a layered structures of the conducting ET layers. ET means this molecule, ET layers, and the insulating anion layers like the cuprates, and the block layer, thin block layer in this case, and thick conducting layer in organic materials. And in this is the in-plane structure. This ET forms a dimer. This dimer forms an anisotropic triangular lattice. So isosceles triangular lattice. And this lattice is simply modeled to this anisotropic triangular lattice, characterized by two kinds of transfer integrals, T and T prime. By changing anion X, we have several materials with different anisotropy, T prime over T. Today, I'd like to compare the properties of the two materials. One is the nearly right triangular lattice, this one, T prime over T is nearly unity. The other one is T prime over T is 0.75. So this is deformed triangular lattice. So triangular lattice and deformed triangular lattice. And this triangular lattice shows quantum spin liquid behavior, and this deformed triangular lattice undergoes anti-ferromagnetic all at low temperatures. Please take a look at the old data of these materials. In deformed triangular lattice, this is NMR spectra, a proto-NMR spectra. You see this single line at high temperatures split below 27 Kelvin. This is the clear indication of the anti-ferromagnetic ordering. And please take a look at the left-hand side figure. This is spin susceptibility as a function of temperature. And spin susceptibility gradually decreases. And then below 27 kelvins, shows a very steep increase. This is the indication of the anti-ferromagnetic order with a spin canting, which is discussed later about the spin canting. Okay, but the triangular lattice does not show any change of the NMR spectra. This double peak comes from the nuclear dipole interaction, so it's not related to the electron spins. The important point, what does matter is the change or not in NMR spectra. So this material does not show any change in NMR spectra with temperature variations. And the spin susceptibility also shows no anomaly, very broad peak formation against temperatures. So first issue arises from the comparison of the night shift versus magnetization in the paramagnetic state, nominally paramagnetic state. And usually night shift sense the local field at nuclear site under the magnetic field. Under the magnetic field, electron spins generates the magnetizations under the magnetic field. In paramagnetic state, which magnetization is usually proportional to the applied field. The magnetic, okay, assume you apply magnetic field along the z-axis, okay? So usually in the paramagnetic state, the magnetization is also appears only along the mz, z-axis. So no mx and my components, no perpendicular components in the conventional paramagnetic state. So the night shift should be proportional to the magnetization. So we usually say k chi proportionality, which is holds in conventional paramagnetic state. However, please take a look at the data of the anti-paramagnetic system case. Temperature and the spin susceptibility here. Red symbol shows the spin susceptibility gradually decreasing, as I showed in the previous view graph, and then nail order curves and the spin counting here. And night shift is indicated by the blue symbols. Two quantities are not scaled, completely different behaviors. But this is very reasonable because there's a Jaroszewski-Mollier interaction in this system. And this is the implant structure again. The spins are sitting on the dimer here, and on the neighboring dimer, another spins are sitting here. So this adjacent spins has no inversion symmetry. In such a case, the Jaroszewski-Mollier interaction works, even if it is very small in organic materials, but there is. So in this case, even in the paramagnetic state, the application of the uniform magnetic field generates staggered effective field. Simple consideration explains these situations. Okay, this is a two site. This one site, please consider this site corresponds to this site, and the neighboring site, for example, this site. Okay, no inversion symmetry between them. Okay, if you apply magnetic field in this direction, in upper directions, and in the paramagnetic state, and usually magnetization should be aligned along this line, yeah, green curve and green arrow, red arrow. However, if the dm vector is perpendicular to the screen, in that case, this spin and dm vector gives a perpendicular field in the neighboring site. This is due to this dm term. So this spin should align, yeah, and also the same situation occurs here. So self-consistently, finally the orbital spins should incline against the applied field. So in the presence of Jaroszewski-Mollier interactions, even in the paramagnetic state, the staggered component appears. And this is the mean field calculation of the staggered field is increasing as a function of temperature. It's the nail temperatures. So increasing staggered component increase. So this mx, my increasing toward nail temperature. So this divergent increase of the night shift is this component. So such a kind of the in such a kind of the copper type molecular arrangement, it is very reasonable that the Jaroszewski-Mollier interactions gives the gives a no KK proportionality. However, please take a look at the right-hand side figure. This is the spin susceptibility indicated by red open circles, and a night shift, and it's a blue or green symbols. It's invisible, I'm sorry. But anyway, these two quantities are mutually scaled. This is very funny. This is very strange. in every couple type antiferromagnetic mop insulators, every material shows no K-Chi proportionality, but only the spin liquid material shows good K-Chi proportionality. How to explain this? One simple model idea is the spins are not localized. And such a consideration is varied for the localized spins. If the spins are itinerant, in that case, the Zariski-Mori interaction doesn't work. So this non-proportionality, no K-Chi proportionality suggests that the spin stuffs are itinerant. Okay, second issue is the so-called 6 Kelvin anomaly. And this spin liquid material shows some anomalies at 6 Kelvin, and that appears in specific heat, and thermal conductivity, and expansivity, sharp anomaly, and ultrasound velocity, and dielectric functions. So this material shows some thermodynamic anomaly around 6 Kelvin, which is called 6 Kelvin anomalies. Let's take a look at the magnetic properties around 6 Kelvin. This is the carbon-13 NMR spectra. In this experiments, we apply magnetic field along the layers. In this field configurations, we see we have two NMR lines. Each comes from the each carbon sites of two carbon isotopes within the molecules. And at lower temperatures, the line shape changes. The important point is that below, say, 6 Kelvin or at lower temperatures, the two peak structure is gone. This is due to the spin susceptibility decreases. Because this black line indicates the origin of the night shift. Namely, this black position of the black line corresponds to the 0 night shift. So all of the lines nears this origin of the night shift. So this means that the local field vanishes at low temperatures. Not vanishes, decreasing, steeply decreases. And at the same time, the line broadening occurs. So the properties are summarized by the two features. One is the steep decrease of the decrease of the local field, average local field. And at the same time, the very steep broadening of the animal line widths. So inhomogeneity occurs below 6 Kelvin. And this is experiments under the 8 Tesla. So anomaly is 6 Kelvin. So we increased the applied magnetic field up to 16 Tesla. Okay, you see, the NMR spectra is complicated depending on the angle, field angle. The angle is the angle against the power direction is changed from 0 to 36 kelvins. But behavior is essentially the same. The several positions line appears depending on the different hyperfine coupling constant. But the situation is the same for all lines. This line has a positive hyperfine coupling constant, but this line has a negative hyperfine coupling constant. However, at low temperatures, all of the lines converge to the night shift 0 positions. This means that the same situation as I explained before. So below 6 Kelvin or lower, the local field is steeply decreases, and then inhomogeneity occurs. This depends on at all angle. And for example, for this angle, we could analyze the line profile to give to yield temperature dependence of the spin susceptibility, like this, 16 Tesla, temperature and the spin susceptibility, which is deduced from the spectral analysis. Okay, you see the spin susceptibility sharply decreases at low temperatures, maybe around 6 Kelvin. In this case, seemingly the spin susceptibility vanishing small. Okay, this may suggest that the spin quantum spin liquid has an instability to the singlet grants, singlet formations. An important point is this anomaly is very robust against magnetic field up to 16 Tesla. Phenomenon occurs 6 Kelvin, but the 16 Tesla does not affect the transition temperatures. How to understand these experimental features? Let me summarize the experimental features. It's the absence of Jaroszynski Muller interactions, seemingly absence of DM interactions, may suggest that the iterant spins, maybe the spin from surface, is one candidate. And another other anomalies is the maybe square anomaly may suggest that the instability of spin quantum spin liquid into the singlet states and this is very robust against magnetic field, and then at the same time, inhomogeneous local field occurs. So these puzzling features may suggest in a simple-minded person like me, an FFL state of the single spin unpairing. And this spin from C and normalic state may suggest that the emergence of the occurrence of the spin unpairing. And this anomaly is very robust against magnetic field. And then in inhomogeneous generation of inhomogeneous local field is consistent with the emergence of FFL state. In the FFL state, such a cartoon is also valid in the pairing. So almost all, this is a cartoon for the FFL superconductors, but I think my speculation is a similar thing occurs may occur in this system. So most of the spins are forms as singlet, but imbalanced spins, namely unpaired spins, are there, and this may give some inhomogeneous local field. Okay. This is my speculation, not evidence. This should be explored theoretically. And okay, this is the a part of list dealing with the theoretically the spin instability. Next topic is the on doped spin liquid. We have doped triangular lattice. This material. This material has non-stoichiometric compositions in insulating anion layers. If the content of mercury is 3.00, in that case, this material is a mod insulator. Okay. And but this 11% missing content provides holes to the conducting rays. This is the this provides holes, additional holes, so hole doping. Please take a look at these figures. Spin susceptibilities normalized to J for two materials. This is a spin liquid non-doped materials, blue symbols. And red symbols indicate the spin susceptibility of this 11% hole doped systems. The two materials show nearly the same spin susceptibilities. However, doped materials shows a good metal. So a charge degrees of freedom shows very the dramatic change. However, the spin sector does not change. So these doped hole materials can be regarded as a doped spin liquid materials. Okay, time is running out, so I should be left in a hurry. Okay, this is the pressure dependence the Hall coefficient. Please take a look at the low temperature behavior, 10 kelvins. Low pressures, the Hall coefficient is large. This means that the density of the holes is very, very small. However, this at high pressure regions, the many calories. So I think that it is around 0.5 kelvins. Some changes occurs from the small number, low calorie density liquid to a high calorie density liquid crossover occurs. And the exponent of the resistivity changes from here to here. This is the exponent. The exponent is the unity. This unity changes to the 2 if you apply pressures. So this is the non-from liquid crossover occurs here. Okay, associated with this crossover, and the superconductivity also shows crossover from the BC to BCS. By upper critical field measurements, we could extract the coherence lengths. Yeah. This material shows a superconducting dome. Yeah. This is the crossover, non-film liquid to film liquid crossover on here at high temperatures. And the coherence length is very short here. And this is the inter-pair distance of Cooper pairs is comparable. This means that this pairing is like a BCS, a BC. But in this case, in the high pressure regions, the many Cooper pairs are overlapping. So BC. So this is KF Guzai, coherence rings. Guzai means coherence rings. Guzai is 1 or 2 or 3 of the order of unity in these pressure regions, low pressure regions. So BC to BCS crossover occurs in this materials. Okay, this is a third topic, not criticality. And the DMFT is a long business of our organizers and my chair. This is the next speakers, Rorik and Hannah and Brad, who performed the calculation of the resistivity around this crossover regions of the mode transitions. This is the phase diagram deduced from the well-known phase diagram deduced from the DMFT, multi-threading phase and the from liquid phase. This crossover transition have the terminal point. And in these regions, and they showed theoretically the resistivity shows 2 universal scaling behaviors in the insulating side and the metallic side here. We did the same thing in experiments, okay, for 3 materials. The 3 materials, this one, each of which have different phase ground states. This material has a spin liquid model insulator and superconducting in the metric side. But this material is anti-filament model insulator and superconducting phase. And this material is spin liquid model insulator and normal metal in the insulator. So the ground states are different for these 3 materials. However, we examined the transporting. We measured the transport. And we examined the scaling according to the Hannah and Brothers method. And this is experimental data. This scaling behavior for this scaling for this material. The right-hand side view graphics for this one. So all of these 3 materials are seemingly different in phase diagram, but the scaling holds, and the Z new value is nearly the same. So we did X-ray experiments, but in this case, X-ray induces disorder in the materials, X-ray and disorder here. And this is a phase diagram of cartoons, and we irradiate X-ray to these materials, and this is the irradiation time. So this critical endpoint, yeah, is decreasing sharply against the radiation time. And then magnetic cooling is also decreasing, and superconducting temperature is also decreasing. This is the effect of the disorder. But interestingly, the disorder is not so strong. It's a very, very weak disorder. We can quantify the strength of the disorder by monitoring the residual resistance in the metallic side. From this residual resistance, we can reduce the mean distance between the disorder centers. For example, okay, 1 or 2 minutes, okay. The mean distance between the disorder centers is 200 or 300. So very sparsely distributed disorder. And such a very weak disorder, we still observed a very good scaling. The exponent is nearly the same for all the case. It's a pristine crystal, 50-hour radiation and 70-hour radiation, and the critical endpoint is decreasing. However, the scaling, the similar scaling holds. But this scaling, the quantum critical region is downs with increasing disorder. Okay, and so this is last graph. This is we are here, the weak disorder regime, and quantum critical region goes down in energies by introducing disorders, and this is the critical exponent Z nu of 0.5 means that this transition, metal-insert transition, is driven by infraction. But if we increase more disorder more and more, maybe this is separated to the two. It's a metal-insert transition and magnetic transitions. And in these regions, maybe the Popovich deduced that obtained the Z nu of 2. It's which is exponent of the disorder dominated exponent. So we think that maybe we may see some change from this value to this value if we increase this. Okay, let me summarize my talk. I talked 3 issues. One is the spin liquid issues, the spins maybe itinerant, and the spin liquid shows instability. Sorry. Instability, and this is a maybe the singlet formation with a couple of state, and we have a doped spin liquid, and quantum criticality is affected by disorder, and disorder unveils mod quantum critical behind the first voltage. They are micro. Thank you for your attention.
Thank you very much.
Yeah. I have many questions, but I'm going to try to ask 2 questions very quickly. So the first one is, what is the role of the lattice near the critical endpoint of the mod transition in the material? And the second question is, if you go closer to TC, away from this regime where you demonstrate quantum scaling, do you have the standard scaling associated with the critical endpoint?
Let me just repeat these questions because of the Zoom. So the first question is related to the lattice degrees of freedom and what is the lattice doing. And the second one is, if you get close to TC, critical endpoint, is the scaling modified?
I'm sorry, I can't clearly hear you. First one is the role of this lattice.
Yes, the role of the lattice is the first question. The second question is
in what? In what topic?
Yes, at the mod transition.
Mod transition, okay. I think that the lattice is very, very soft material, soft in organic materials. I think that it's lattice modulation occurs associated with mod transition. But I think that in the topics of this namely the quantum critical behavior of the transition, is a phenomenal occurs in the crossover regions. So I think that in the quantum critical issues of the transitions, I think that the lattice, the low-level lattice is secondary, I think.
Okay. What about the behavior very close to TC?
So I can
behavior close to TC.
Close to TC. Okay. In close to TC is maybe lattice makes everything classical, I think. And there is a very debate about this critical exponent around the final temperature critical point is, and it's a still under debate. But I think that the just on the critical final temperature critical point, it's a lattice makes everything classical, I think. But I did not touch these issues on this talk.
Okay, very good. So, any other questions? Other questions? Okay, great. So we are on time. Let's thanks Kanoda-san once more.